Hello again. In this video we'll continue with example 6, now the section B. We have to implement the same function, but this time we have 4-to-1 multiplexers, means 4 data inputs and only 2 selections. Okay, to do so we are going to use we start in the same way. I'll copy the kernel map that we used before. Let's see. And okay, we'll copy here of this map. Let's eliminate the things that we don't need from here. Okay. And we'll repeat it. Actually, we use the same idea than before. We'll generate our function using a multiplexer, and we'll find in the map what's the inputs for the multiplexer that I need in order to get to the right function. Okay, so but now this time I need to use 4-to-1 multiplexers, which is something like this. Okay, these are multiplexers with only 2 input selections. So we have 4 data inputs, 2 selection inputs, and yes, 1 output. I want my function to be generated here. These are the weights of the inputs, 0, 1, 2, 3. Okay, this is a mux 4-to-1. Okay, now this is the map of my function. So I start in the same way. We have two selection inputs. So I select 2 of the input variables. Actually, I can select any input variables for the function. Okay, I will just select W and X, but I may have selected another combination. It's not really important. So W and X. So the idea now is that I have to find out in the map where the pieces of function, the residuals that we have left when we use a multiplexer. I remember now in this input, because this input is selected when W is 0 and X is 0, I need to put here the value of F in this case, Y and Z. Okay? This is to say the value of F when W is equal to 0 and X is equal to 0. Okay, if I put this value here, it will make the right function. If I put the value for W equal to 0 and X equal to 1, it will get the right value. Okay, so it's just a matter of localizing the right residuals. So now I go to the map and I say this is, to make it easier, we call this F0, we call this F1, F2, and F3. Okay, where's F0 in my map? So it's the function in case that W and X are 0. This is the first column here. This is all this portion of the kernel map. Okay, this is F0. The next residual, F1, is the portion when Wx is 0, 1. This is all this part of the map here. Okay, this is F1. The next one is when WX are 1, 0. 1, 0 is here. Because we are using a kernel map, you have to be careful with the order. So this is F2, and finally this is the map for F3. Okay. Now the problem now is that F0 is now a function only of y and z, but it's not a simple function, not something that I can write with. It's not a single variable. Okay. If you take a look to F1, F1 is easier, because if you take a look at F1, when y is 0, F1 is 0. When y is 1, F1 is 1. So F1 is the expression for F1 is it's equal to C. Okay, so actually we can write C here. This is just C. I'm going to put it a bit bigger. Okay. So that's finished, but we don't have a simple expression for F3 or a simple expression for F2. We have to simplify, okay? But now we are going to use only multiplexers. So it's easy with the multiplexer. It means now we can use another multiplexer in turn to implement F0. So it's just a matter of drawing a new multiplexer here. Okay, for F0. And draw the connections. Okay, so now F0, F1 all depend on y and z. I select y and z, the remaining variables that I have not yet used for the next level of multiplexers. These will have 1, 2, 3, 4 inputs, 0, 1, 2, and 3, 1 and 0. So I will use this new multiplexer to implement F0. Now, what do I have to put in the inputs there? This is F0 now. This is only this part of the map, F0. In order to implement F0 here, when y and z are 0, 0, this input will be selected. So I need to put here the value of F0 when y is 0 and z is 0. This is the same as saying that we have to put the value of f when y and z are 0, 0. This is F0. And additionally, y is 0 and z is 0. Okay? Z is 0. And I can find this value in the map. This is this value here. This portion here is this one here. If you wish, I can call it F00. I can call it F01. Okay, the residual one of the residual F0, something like that. Okay? F01 is the value of F0 when inputs are 0, 1, which is this one here. Okay, this will be F00. This will be F01. This will be F02, and this will be F03. Okay, so it's just going through the inputs and say I need the value when for number 2. Number 2 is 1, 0, so I need the value when y is 1 and z is 0. Y is 1, z is 0, so it's 1. Okay, this is F02. So we just copy the values there. F00 is 1, F01 is 1, F02 is 1, and this one is a 0. Okay, so I have solved F0. So basically, the first multiplexer divides my kernel map in 4 kernel maps, smaller kernel maps. And because these kernel maps are not simple expressions, are not a single literal, I use another multiplexer to divide this kernel map in smaller pieces, in 4 pieces that now are just ones or zeros. Now, I will move this a bit lower here, because for F2, I need another multiplexer. So I do it in exactly the same way. I can draw another multiplexer here, and I will need still another multiplexer for F3. So I will draw another multiplexer here. We take these variables and we will use the same variables for all multiplexers at the same time. Okay, and now we simply complete our design. 1, 2, 3, 1, 0, 1, 0. Okay, this is the multiplexer producing F2, multiplexer producing F3. And now again, F2 is here. When Y and Z are 0, 0, I select this one. So I will put this value. F 0, 1, for 0, 1, I need a 0. For 1, 0, I need a 0. And for 1, 1, I need a 0. And yes, in this case, just copying the values from the table in the right order. Okay, the 0, 0 is a 1. The 0, 1 is a 0. The 1, 0 is a 1. And the 1, 1 is 1. And that's it. That will be the solution using a 4-to-1 multiplexer. This way you can implement any function, no matter how many variables it has, using only multiplexers. No matter how simple or how small, how big your multiplexer is. Because if your multiplexer is small, at the next level, your residuals will be complex functions that you can solve using another level of multiplexers. Okay. Sometimes, like in the previous part of the exercise, if your function has 4 variables and you have used 3 variables, some of the residuals may be simple functions like a literal, complemented or not. Okay, in that case you don't need to use more multiplexers because you may assume that you have an inverter. Okay, in this case, after the second level of multiplexers, this multiplexer eliminates W and X from the expressions of the residuals, and this level eliminates Y and Z from the expression of the remaining residuals. Okay, so the remaining residuals do not depend on any variable. That's why they are just ones or zeros. Okay, and it's just a very mechanical process. It's a bit tricky, but just a way to you can apply it no matter how complex is your function to implement any function. So, and as I explained in the previous example, FPGAs use lookup tables that basically use this method to implement any function using multiplexers. Lookup tables in FPGAs are not so big. They are not incredibly big. Lookup tables depends on the multiplexer, on the FPGA, but they may have 16 entries or 4 selection inputs, or a bit more or a bit less. Okay, but it's not a problem, because even if your function is more complex, you can combine different lookup tables to implement more complex functions in the same way that you can combine a different multiplexer to implement any function, no matter how complex it is. Okay, that's it. Thank you.